Hello and welcome. In this tutorial, I will demonstrate how to perform, interpret, and report a one-way between subjects ANOVA in SPSS. A one-way between subjects ANOVA is the appropriate analysis to run when we have one between subjects factor. That between subjects factor has three or more levels, or in other words, we're comparing three or more group means to one another. The dependent or outcome variable is quantitative in nature, and the assumption of homogeneity of variance has been met. For this tutorial, I created simple hypothetical data based on a classic study done by Loftus and Palmer published in 1974. In that original study, they had participants watch a video of a car accident in which the cars were traveling at a rate of 20 miles per hour. Afterward, participants assuming the role as an eyewitness were asked questions about the accident they saw in that video. For one question, participants were asked about how fast the cars were going when they hit each other. Loftus and Palmer manipulated the wording of the question to see how it affected witnesses' perception of that car accident. In particular, they changed the verb hit and replaced it with other words such as contacted, which would suggest maybe less speed, or smashed, which would be suggestive of maybe more speed. Here I built out a similar between subjects data set in SPSS, comparing three verbs in questioning along with a speed estimate given by the participants when asked the question about how fast the cars were going. However, the data in this example was made up and simplified to allow for easy hand calculation of the ANOVA that we're going to run, as well as interpretation. So as we'll notice at different points in this tutorial, the data will look almost too perfect, and this tends to occur with hypothetical data that's made up, and real data never tends to be quite this clean. So assuming in a similar study that we ran, similar to the one by Loftus and Palmer, we had 15 participants that watched the video. 5 of them were asked with the question phrasing, how fast was the car going, or were the cars going when they contacted each other. 5 other participants were asked how fast the cars were going when they hit each other, and 5 other participants were asked how fast they were going when they smashed into each other. So if we look at our data set here, we see that we have 15 participants. They were in one of 3 groups, depending on the question phrasing they were given, and each of them gave a speed estimate to that question. If we go ahead and move over to the variable view, we can see those two variables input here. We have the question phrasing, which included the verb used in that question, and there's 3 different groups or values: contact, hit, smash. Because we're comparing 3 different groups, this is the reason why we would run an ANOVA in this instance as opposed to a t-test. Had we just compared maybe 2 different verbs that were used in questions, then an independent samples t-test would be appropriate. But because we're comparing 3 in this case, we would want to run an ANOVA. And then we have our dependent variable of the speed estimate, which is a quantitative interval scale ratio measure. So to go ahead and run the one-way between subjects ANOVA, we would go to Analyze, Compare Means, and we'll see all the way on the bottom there the option of the one-way ANOVA. So Analyze, Compare Means, one-way ANOVA. Once we get to the one-way ANOVA, we'll see that dialog box here, and we have our 2 variables in our variable box on the left. Our factor in this case is the question phrasing, which has the 3 levels of contacted, hit, or smashed. And our dependent variable is the speed estimate. So we'll move our factor into the box below, and our dependent variable, our dependent measure in the box above. Then we have 3 menu dialog buttons that we can push to specify different aspects of our output. If we had a priori hypotheses about what to expect, then we could do focus contrast by using the contrast button. In most cases, running focus contrast is preferred because we do tend to have specific hypotheses about what we expect to find, and that controls the pattern of results we're looking for, leading to less likely for us to conclude in erroneous results. However, it's a little bit more complicated to run focus contrast, so we're going to skip that for now. We're going to focus on conducting a post hoc test. So keep in mind that really we should only be interpreting post hoc results if our ANOVA was significant. So should we run this ANOVA and we find that we have a significant F ratio, that would indicate that the question phrasing did impact the speed estimate given by participants. What we don't know from that significant F ratio in our ANOVA is where the differences between groups lie. And in order to determine that, we would either want to do that focus contrast or run post hoc tests that compare means, much like a t-test would. The difference between a post hoc test and a t-test is that post hoc tests, should we choose the right correction and type of post hoc test, helps to control for inflated experiment-wise type 1 error rate. So it allows us to reduce that overall type 1 error rate. So in particular, if we have equal sample size in each condition, which in this case we have 5 participants in each group, Tukey's is a good conservative post hoc test to use. Other recommended ones, Bonferroni is good. LSD just compares the means itself, so you would want to apply a correction to that afterwards. So we'll just go ahead and run the Tukey test since we have equal sample size, and go ahead and click continue there. We also have other options in which we can specify. So here in the options menu button, we can see a few things. The first one allows us to get descriptive statistics comparing the mean for each of our groups, as well as standard deviation and standard error. We'll skip fixed and random effects for now, but we do want to also test to make sure we met the assumption of homogeneity of variance. So here we're given the Levene's test for homogeneity of variance and output there. And then should we not meet the assumption of homogeneity of variance, it gives us two other options in either the Brown-Forsyth or the Welch to request as alternatives should we be concerned about violating the homogeneity of variance assumption. So we'll click those both. Finally, we can also ask for a line plot of the means to help us look or visually view any pattern of results that we see in mean differences between the three groups. So we'll go ahead and click that as well, and then click continue. Once we have that all specified in both our post hoc and options here, we can go ahead and click OK to run this analysis. As we take a look at the output for the one-way ANOVA, we'll go ahead and move that up there. We see the descriptives table that we requested comparing the three different groups means, as well as giving us an overall total mean, the standard deviation for each of those, and this is where I was saying that made up data looks a little too clean. So here we're obviously not going to have any problems with homogeneity of variance because all three have the exact same standard deviation. So we're going to see really clean mean differences between the three groups should they exist. We're also given 95% confidence intervals and minimum maximum values for each. As we could have guessed, because there's no difference in variability across the three conditions, the homogeneity of variance test was not significant, having a Levene statistic of 0.000. There's no variability across conditions. They're equivalent in the samples of 5 participants that we have. So we don't have to worry about interpreting alternative tests such as the Welch and Brown, but we can use this ANOVA summary table here. And this is going to look very similar to summary tables that you might have seen when we've done hand calculations of the one-way ANOVA. And it's very simple and straightforward. So the ANOVA is calculated based on variances, and the variance is determined from 2 sources. The sources are either between groups, which is what is the systematic differences between groups that we hope is due to whatever the manipulation or core difference between those groups being compared is. So in this case, we're assuming that variability between groups is due to differences of the verb used when given the question on the speed estimate. Within groups is the variability we observe within each particular group. This is what we use for our error variance term in a between subjects ANOVA. So we would expect roughly similar within subject variability across all 3 conditions. And what we are computing when we're computing the F ratio is a ratio of the variability between over the variability within. Should we have more explained variability or between subjects or between groups variability that helps us see systematic differences between groups compared to error variability or within group variability, then our F ratio should be higher and our ANOVA should be significant. If we have a lot of error or noise within groups that makes it hard to see between groups difference and our between group variability is low, then our F ratio will be lower and it'll be less likely that our ANOVA output would be significant. So here we have the sum of squares, the degrees of freedom associated with each. So we calculate the degrees of freedom for between groups by taking the number of levels, 3 in this case, contacted, hit, and smashed, and subtracting that from 1 to get 2 degrees of freedom. The mean squared or the variance is then calculated by taking the sum of squares divided by those degrees of freedom to get the mean squared. The within group sum of squares is presented here, and we calculate this degrees of freedom by taking the total number of participants in our sample or in our study, which was 15, divided by the number of levels, which was 3. So 15 minus 3 is 12. And we can calculate the within groups variance or mean squared by taking its sum of squares divided by the degrees of freedom to get 2.5. Lastly, the overall degrees of freedom are calculated by taking n minus 1. So in this case, we had 15 participants, so the overall degrees of freedom would be 14. We calculate the F ratio by taking the mean squared between divided by the mean squared within to get an F of 56 in this case. And as we can see here, this is highly significant. So a couple things to note here about this unique case. First, when we compare this to other statistics like the T statistic, a number of 56 seems really, really large. And it's for F, it is capable to have much larger values than we would have seen in a T test because we're working in squared units. In addition, an F ratio will never be negative, once again, because we're working with squared units. So when we look at the F distribution itself, it's somewhat positively skewed as far as the values we would see, and they're all over 1, basically. So no effect would be an F of 1. As we get higher F ratios, then it's more likely to see an effect and be significant. Another thing to note is significance is never exactly 0.000. What this means is it's at least less than 0.001. And if we wanted to, we could go ahead and click in here and see what the actual value is, which is very, very small. So we know it's significant. It's well below 0.05. So what we do know is that the verb that was used within a question does have an effect on speed estimate. We just don't know where those differences are. In order to interpret that, we need to go down to the post hoc tests to see which groups in particular were different from one another, or which verbs in particular led to different speed estimates. So in this case, what we see in the multiple comparisons is in this case, each verb or group is being compared to one another. Should that be significant, we're going to see a little asterisk by that mean difference within the table here. So in particular, it looks like contacted had a significantly different mean mile per hour speed estimate of how fast the cars were going when they smashed than the word smashed. And hit also had a significant speed estimate difference from smashed. And if we look at the smashed one, both of these are different. If we're looking at the mean difference here and seeing that it's positive, that means the estimate given for smashed was greater than contacted and was also greater than hit. And we can also go back up and look at the means to see this as well. So the mean estimate given for speed for when smashed was used in the question was 29, whereas it was 21 miles per hour for hit and 19 for contacted. So while while smashed led to faster speed or higher speed estimates than contacted or hit, when we compare hit and contacted to one another, that mean difference of 2 was not significant. It was 0.155. So there was not a significant difference in speed estimates between hit and contacted in this case. Finally, we can see those means plotted on a graph. This isn't perfect because the scale isn't great here, so it may over-exaggerate differences that we see. So you might, whenever you produce these, you might want to look at the scale and change it to be more accurate in how it's viewed or pictured. Finally, out of all the ANOVAs, the one-way ANOVA is the only one that doesn't allow you to request an automatic measure of effect size. So for ANOVA, we can calculate the effect size of eta squared by taking the sum of squares between groups divided by the sum of squares total. So we can, in this case, we can take 280 divided by 310 to get the eta squared of 0.90. In other ANOVAs, as we'll see in other tutorials, you can request that and it'll be put right in your SPSS output. Keep in mind that you could also calculate individual effect sizes for specific group differences. So if we wanted to calculate the R or the D for smashed compared to contacted, we could do that by using the formulas we used before within the t-test. Finally, we can go about showing how we would report this in an APA style report. So first off, for reporting the F statistic, we would, in standard statistical notation, we would report capital F italicized. In parentheses, we would actually put 2 different degrees of freedom. So we'd put the degrees of freedom between first, so 2, comma, then the degrees of freedom within 12 parentheses equals then we actually put the F ratio that we obtained of 56. In this case, because the p-value is well below even 0.001, we can put p less than 0.001. And then after that, we could put comma and then include the measure of effect size of eta squared, which was 0.90. If we were to write it up overall and interpret it, it might look something like this. So a one-way ANOVA compared participants' mean speed estimate of a car during a witnessed accident after hearing a question phrased in one of 3 ways. Participants were asked how fast car A was going when it contacted, hit, or smashed car B. The test indicated that the wording used to ask about the accident influenced participants' estimation of how fast the car was going during the accident. Notice here how the interpretation of the significant ANOVA doesn't suggest where the differences are, just suggesting that the independent variable had an effect on the dependent variable. And in this case, F with 2 and 12 degrees of freedom was 56. The probability of obtaining an F that large if the null hypothesis were true, if there were no differences between any groups, was less than 0.001, and this is a very large effect size of eta squared. We then report the post hoc test. So a Tukey HSD post hoc test showed that the mean speed estimate when the question was phrased in terms of car A smashing into car B was significantly higher. So it was higher for smashing than contacted or hit, and we report the means and standard deviations for each of those there. And then we also include the fact that no significant differences were found between contacted and hit. Finally, if you want extra help on the one-way ANOVA, you can go to Help Topics. Once you bring up the online help menu, you can go to Statistics Base Options and then go to the one-way ANOVA. And there will be a lot of extra help there or refresher if you need help on the one-way ANOVA. Thank you very much for following along with this tutorial.